Hello everyone, thanks for being interested in our paper. I am Bahar Asgari and I'm so excited to introduce Maia, the study that focuses on accelerating matrix inversion, an essential and challenging operation in several application domains from scientific computing to social networks and recommendation systems. Since matrix inversion is a memory-bound task, it has the potential of being implemented near memory to efficiently use high memory bandwidth. However, data dependency patterns in the common matrix inversion algorithms limit memory bandwidth utilization. Let's first take a look at this challenge in more details. Let's say that we want to invert matrix A by using the lower upper or LU decomposition method. The decomposition part of LU method is more straightforward and parallelizable compared to the invert algorithm, a very simplified version of which is listed in this slide that consists of an outer loop and two inner loops. As this slide shows, in each of the inner loops, an entire column of the invert matrix or IA and the triangle of A are read, and simultaneously the same column of IA is updated. As a result, the iterations of I are dependent. Therefore, we must process the rows of A sequentially. In other words, reading and updating the same column of IA potentially creates a data dependency that prevents further parallelism and limits full utilization of memory bandwidth. Even the most optimized FPGA implementations in prior work can parallelize matrix inversion only up to a certain degree. More specifically, to parallelize the iterations of k by a factor of n, a common approach would be to unroll the iterations of k by a factor of n and to interleave the elements of A into n partitions of BRAM so that we can access them in parallel. Then we can pipeline these chunks of size n. In such an implementation, however, there is no pipelining or parallelism across the rows. Therefore, the time to process half of A grows with the number of rows. And if the number of rows doubles, the time to process it would increase approximately 4 times. For more details about our baseline, please refer to our paper. To solve the key challenge and improve the level of parallelism in an FPGA implementation, we have to enable parallelism across the rows. To do so, we first break down matrix A into smaller blocks as shown in the figure in the left, in which once we are done with processing A1, all rows in A2 can be processed in parallel. However, you may ask that since we still need to sequentially process all rows of A3, even if we increase parallelism in processing some of the blocks of A, the overall performance would be still limited by the same number of sequential operations that we had before. You are right. Only if we accelerate the sequential blocks, for instance A3, will this challenge be resolved, which is what the key insight of Maia is. In fact, thanks to blocking, the sequential operations becomes smaller now, which allows us to implement them as a small optimized logic with a fixed small latency. To implement our approach, after dividing matrix A into several small blocks, we apply sparse matrix vector multiplication or SpMV on the squares and invert on the triangles. In other words, the main large invert operation will be broken down into several SpMVs and very small invert operations as shown in the figure in the right. Although we increase the level of parallelism and accelerate the sequential operations, there would be still dependencies in between the SpMV and invert operations as the dependency graph in this slide shows. As long as dependencies are not violated, the small SpMVs can be combined together to create a larger SpMV, and similarly 2 small invert nodes and 1 small SpMV node can be combined to create a larger invert operation. In fact, partitioning this dependency graph into the blocks with right sizes and mapping them into compute units in the FPGA gives us the flexibility to optimize our implementation. For instance, let's review 2 possible partitioning and mapping that Maia implements when we put together the graphs for 2 inner loops. In the first implementation, we simply extend the partitioning that we just saw to the entire algorithm as shown in this figure on the left. However, as we can see, one large chain of dependencies will occur because of two consecutive invert operations right next to each other, which would cause a timeline like the one shown in this slide, where step 3 and 4 have to run sequentially. However, we don't have to partition the graph in this way. So in our second implementation, we break down the big SpMV so that we can overlap it with the invert operations. To do so, we also changed our hardware to include two SpMV engines, a small one and a large one, because now we need to perform parallel SpMVs, for instance, nodes 2 and 4, or nodes 12 and 14 in this graph. Therefore, as the timeline shows, our second implementation can overlap more operations and perform the entire graph in fewer cycles compared to the first implementation. The bar chart in this slide illustrates the overall impact of partitioning scheme when the number of columns increases. As we can see, implementation 2 is 1.7 times faster than implementation 1 for a matrix size of 4096. In addition to partitioning, the implementation of SpMV engine also plays a key role in the performance of matrix inversion. Maia also explores two alternative implementations for SpMV. For details about the pros and cons of each implementation, please refer to our paper. Just to give an example, as the figure in this slide shows, to achieve a close to peak throughput, our first implementation for SpMV requires buffering a 128 times 128 submatrix rather than a 64 times 64 matrix for SpMV2. In other words, by utilizing the same BRAM for buffering smaller inputs, SpMV2 achieves about 4.3 times higher throughput. To evaluate Maia, we first describe it in C++ and use it as the input to our high-level synthesis tool, which is Vivado HLS, that we use it for simulations, and we use Vivado for synthesis and implementation. We target an Ultrascale plus Xilinx FPGA on Alveo boards. We set the clock frequency to 450 MHz and verify the functionality of Maia using synthetic data. We use sparse matrices from Suite's sparse dataset for evaluations. Finally, we explore two configurations of Maia, implementation 1 plus SpMV1 and our second implementation plus SpMV2. Let's first compare the execution time of the two configurations of Maia with the baseline optimized implementation, in which, as we explained before, parallelism and pipelining is fully implemented only within the rows but not across them. As we can see here, because of more overlap tasks at hardware and better load balancing among the level of reduction tree, our second implementation always works more quickly than the first one. Of course, depending on the pattern of sparsity, which in turn defines the opportunity for cross-row parallelism, pipelining, concurrency, and load balancing. The first implementation performs matrix inversion up to 2.99 times faster than baseline, while our second implementation provides a speedup up to 4.8 times faster over the baseline. The greater speedup of our second implementation comes at a cost of more resource utilization. As the figures in this slide suggest, it utilizes more lookup tables, flip-flops, and DRAM blocks because of the following reasons. First, although each compute unit is simpler in our second implementation, it uses some additional resources to arrange data before sending them to the compute units. The second reason is that our second implementation must also coordinate a synchronization across the compute units. As the figure in this slide illustrates, implementation 2 consumes about 1.8 times less dynamic power compared to implementation 1, mainly because of signals and logic used for more complex compute units. On the other hand, we see that the static power consumption of both implementations are almost the same. Therefore, in total, implementation 2 consumes only about 1.08 times less power compared to implementation 1. Thanks for watching. If you have any questions, please feel free to reach out to us.